All right, questions. We're not having a quiz. We are not having a quiz. You're all ready. We'll always be ready. Always be ready. But we should have one next week, and it might come on Monday, okay? It might. We'll see. May or may not. So any questions over homework? Which one? Number 40? Let me look at it. Okay. I didn't do this one for you. I left it for you.
That was the one with the parallel line, right?
Yes. Yeah, this is worth talking about. All right. So this is number 40 in the homework for the basic differentiation formulas. And it says, look, you've got this curve. It says, find the equation of the tangent line to this curve that is parallel to this line. So let me give you some idea of what's happening here by graphing it for you, all right? That'll help us see what's going on, I hope. Hopefully this will graph x. What is that? 1 plus 3x? Oops, sorry. All right. So the red curve is this x root x. And the blue, or I don't know if that looks blue to you, but this one is this line. And what we're asked to find is the equation of the line that is tangent to this red curve and parallel to that curve. So somewhere on this curve, not here, right? Because that tangent line is not parallel to the blue one. But somewhere on here, there should be, I don't know where it is, but there should be a tangent line that runs parallel to that one, right? And we want the equation of that tangent line. So what can you someone who did it, who has an idea what to do, want to help? No? What can you tell me about this tangent line I'm looking for? Can you tell me anything about it? What?
It should have a slope of 3.
It should have a slope of 3. Because it has to be parallel to this line, right? If it's parallel to this line, this is the slope of this line. Y equals mx plus b, right? It's written backwards. But I know that the tangent line I'm looking for must have a slope of 3. Good. Now, the slope of the tangent line of this curve is the derivative of it, right? I know that the derivative of that must be 3. And that's an equation I'm going to be able to solve. So here's what I want. I want the derivative of that function to be equal to 3. Now, what is the derivative? And we have to figure that out. So how are you going to take the derivative of this?
Well, we know that it's 1 over 2 1 over 2 squared.
1 over 2 root x. I told you about that, right? Yeah. However, you have x times root x, right? That's not just x raised to a power, not yet. What we need to do is first write that as x to a power. So I'm going to rewrite it like this first, and then I can combine those together, right? You add the exponents, and this is x to the 3 halves. Do you agree? Now the reason you do not just take the derivative of this and say 1 and the derivative of this and say 1 over 2 root x is because there's a product. And we did not do that when we had products. In fact, we didn't do anything that had products intentionally because today is about products. Well, we'll see what we do, okay? We have the product rule. So we first convert it to x to a power. That we can take the derivative of. So what is the derivative of this? 3 halves x to the half, right? And we need that to be equal to 3. And that's an equation. We can solve this, right? Understand? No questions?
But where did you get the half again? For the x?
Remember, the power comes down, and then you subtract 1 from the power,
Oh, yeah.
right?
Yeah, so you just need to...
Yeah, I'm not going to write that anymore. It's just going to be... This is going to start to build pretty quickly on itself. So if you have any questions on where something came from, let me know, right? Make sure you stop me. And to solve this, I'm going to multiply both sides by 2/3 by the reciprocal, right? 2/3 here, 2/3 here. I'll get x to the half equals what? When I multiply that times 2/3? 2. Okay. And how do I solve that for x? Square both sides. That's the same as this, right? Square both sides, and you get x is 4, right? Square both sides, not square root. We good? X is 4. So what that's telling me is on that graph, if I go out to x is 4 and go up to that curve that looked like this, that when I get there, the slope of that tangent line is going to be what? 3, right? It's going to be 3. Yes?
It asks for the equation.
That's right. It asks for the equation. I have not given us that. I'm just I'm making sure everyone understands that this 4 is telling us that's what our x coordinate needs to be in order to have a tangent line with the slope of 3. But it wants the equation of that line. So what are the things that you need for the equation of a line? You need a point and a slope. Do we know the slope of the line we're looking for?
Yes.
What is it? 3. So I'm going to use this formula right here. I know that the m is 3. I know that much. Do you know anything about the point? That's right. You know that this point has an x value of 4, right? So you know that this point right here, or this right here, is 4. And do you know the y value?
Well, you can plug and play.
Yeah, that's right. Where are you going to plug this 4 into, though?
The derivative.
If you plug the 4 into the derivative, you're going to get 3.
Okay, then you have to plug into the other equation.
Which one? The original curve, the original x root x. Right? Because that point will live on the original curve. It has to. So plug in 4 into this. Y is equal to x root x. Plug in 4, you get 4 root 4, which is 8. So this right here should be 8. And that is the equation of the line. Now I'll clean it up because there's no fractions in here, so when I don't see fractions, I move on. And 3x, what's that, minus 4? So if I go back over to the computer right now, and I have the computer graph this right here, I should get a line that is parallel to the other line and lives on that curve. So let's see. What is it? 3x minus 4. What do y'all think? Does that look like it's look like that's parallel? You don't see it? All right. this line is parallel to this line and it lives on that curve, which is what we wanted. Does that help? Good. All right, let's get to today's material. When it comes to these shortcuts for finding derivatives, there are 3 critical days where we talk about these shortcuts, and we could rank the importance of these days. Last class was the 3rd most important day. Today is the 2nd most important day, and then on Monday will be the most important day when it comes to the rules. You cannot do today's stuff without last class's stuff. And you can't do what we do on Monday without today's stuff. So make sure that this weekend you spend a lot of time going through your homework, making sure you understand it, so that when you walk in on Monday, you're not like, well, I still need to go back and review that. You have to have it down, or else what we do next week will be very difficult. All right? So we are going to work through what's called the product rule and the quotient rule. Now this is in your notes, it was on the video, it's in your book, but I'm going to write it down anyway because I want to make sure everyone understands it. If you take a function and you multiply it times another function, so if you take some function f, some other function g, and you want to multiply them, and you take that derivative of that new function, right? Because when you multiply 2 functions together, you get a new function. So you take that and you want to know its derivative. There's a way we can get it. And here's the way. You take the derivative of the first function. I'm going to say this is the first function, this is the second function, okay? Listen to I'm going to say a lot of things today. Okay, the language of what I say, pay attention to. I'm calling this the first function, this is the second function. The rule says take the derivative of the first function and then multiply it times the second function, but don't take its derivative. Then add to that the derivative of the second function and then multiply that times the first function without taking its derivative. So it's almost like they take turns, right? First you take the derivative of f, then multiply it times g. So f got the derivative, g didn't. Then plus, then g gets the derivative and f doesn't. And you put those 2 together, add them up, and that's your answer. Now, most students, when they first see this, would love for the answer to just be this. I mean, wouldn't life be nice if that were the formula? Because then all you would have to do if you had a product is take the derivative of each one separately and then multiply the answers. That is incorrect. Very incorrect. And this is part of what makes Cal 1 a little tough, is because when you get to these more complicated functions, the derivatives are not as smooth and easy as you would wish they were. All right, now the book has a slightly different version of this, but I'm going to get to that in a minute. Let me work through some exammples. All right? You may also see me write this down just to be short, like shorthand. You might see me write f dot g equals f prime g plus g prime f, like that. That's the same thing. I'm just not writing f of x, g of x, right? I'm just writing f, g, f, g. That's the same formula. And it really doesn't matter what we use. If I say u times v, then this would be u prime v plus v prime u. Right? It does not matter what letters I use. It's the pattern that's important. All right, here we go. Let's do this one first. Let's say y equals x cubed plus x plus 1 times x to the 4th plus 2x minus 5. Now I'm starting out with this one because if you think back to last class, if this was the only thing given to you, right? We could take the derivative of that, couldn't we? And if this was the only thing given to you, we could take the derivative of that because that's all power rule, right? But these are multiplied together, so it's no longer going to be just derivative of each one, because we have a product right here. Now, could we just expand this all out? Like multiply this through and get it, and then get this big long polynomial? Yes? And then that answer, could we take derivative of each one individually? Yes, we could. And we're going to, after we're done doing the product rule, we're going to do it both ways, and we're going to compare like which one was easier. All right? But I'd like to treat this as a product rule. So I need to identify the two functions I have. So this one right here, that is a function of x. I'm going to call it f of x. And this is a separate function of x, which I'm going to call g of x. Right? And so using the rule, if we have the product of two functions, the derivative should be f, I'm going to write it this way, f prime g plus g prime f, right? That's what it should be. Now, I'm going to write a little bit more. Pay attention to how I write this. I want the derivative of f first, right? So watch how I write this. I'm going to write x cubed plus 1, plus x plus 1, but I need to take that derivative, right? So I'm going to put prime. Just to remind you, I've got to take derivative of f. Then I'm going to multiply times g. So I'm just going to put g here. Then plus the derivative of g. So I'm just writing g down, and then I'm going to tell you take its derivative, and then times f. Do y'all see this? We have f prime g plus g prime f. There we go. Now we go take derivatives. I will show you at the end of class. I will prove the product rule. Okay, because I proved the power rule, right, last class? I'm going to prove the product rule. That way you believe that it actually is this. But it seems weird that it would be that, right? Doesn't that seem like such a weird formula? All right, what is the derivative of x cubed plus x plus 1?
3x squared.
3x squared plus 1. That should be becoming almost automatic for you. All right? And then I have x to the fourth plus 2x minus 5. I'm not taking derivative of that, so I'm just leaving it alone. Plus, now I need the derivative of this one. 4x cubed plus 2. And the last one, x cubed plus x plus 1. There, that's it. That's the derivative.
So that's the derivative when they get multiplied.
Yeah, this right here is a function, right? This whole big thing is a function. Y equals that. I could go type it into my computer. We could graph this, right? This right here would be its derivative. If I graphed it, it would be its derivative. Okay? Now, I'm going to clean this up. One of the things you're going to see today is we're going to do a lot of algebra today. I'm going to clean this up, which means I'm going to expand everything out. All right? So I'm going to multiply first 3x squared through. All right? So let's do that. 3x squared times x to the fourth would be 3x to the sixth, right? Then we have plus 6x cubed, and then minus 15x squared. Okay, so I've passed the 3x squared through. Now I'm going to pass a 1 through, right? 1 through here. So that's just going to give me exactly what was there already. So I just did this part. And then I have to do the same thing over here. Here to here. 4x to the sixth. Here to here. 4x to the fourth. Here to here. 4x cubed. Y'all know what I'm doing, right? Okay, and then now we're going to do the 2 through here. So we get 2x cubed plus 2x plus 2. All right, now we have this big, nasty, ugly polynomial. And let's collect like terms. Okay, let's collect like terms. And I'm going to erase this up here so I can have the answer right here. How many x to the sixth do we have? 7x to the sixth. Good. I like to cancel these out as I go, so I know I've taken care of them. All right. No x to the fifths. X to the fourth.
There was 4 and x.
5. Right, we have one of them here and 4 of them here, so 5 of them. Okay, I've got the x to the fourths out of here. X cubes.
6x to 3 and 4x cubed. That would be
12.
cubed.
We have 6, 4, that's 10, 2 more, that's 12. 12x to the third. Squareds, negative 15, that's it, right? Negative 15x squared. And x's, plus 2 and plus 2, so I have 4 of them. And finally, minus 3, so 2 and then negative 5, so minus 3. Where am I? Right here. There we go. That's the derivative of that function. Now, the reason I did that is because remember I said when I started out that we could use the product rule, right? Or we could have multiplied that all out to start. So let's go back up to the original. We're done, okay? But let's go back up to the original and let's act like we don't like the product rule. We're like, I don't want to use it, okay? I don't like it. So I'm going to do this instead. I'm going to multiply all this out first. So what would happen if I multiply this out? X to the 7th plus 2x to the 4th minus 5x cubed, right? That's what I would get when I multiply my x cubed through. Then I have to multiply x through. So I'd have x to the 5th plus 2x squared minus 5x. And then I have to multiply 1 through. So x to the 4th plus 2x minus 5, right? Collect all my like terms together. Do I have any? How many x to the 7th? Just one, right? X to the 7th? X to the 4th? 3 of them? Is that right? Oh, I forgot the x to the 5th. Sorry, I skipped that. Let me do the x to the 5th next. Just one of them, right? X to the 4th. You said 3? And x cubes minus 5x cubed. X squareds.
4x squared.
Just 2. 2x squared right there. X by itself. Minus 3x. And then minus 5. So that's the original function had you multiplied it out to start. Now take the derivative of that, and what do you get? 7x to the 6th plus 5x to the 4th. 4 comes out, 12x cubed, right? 3 comes out, negative 15x squared. 2 comes out, 4x minus 3, 0, right? So it's this. So we got the same answer both ways, right? Understand?
Yeah.
Which way do you think was better?
In this particular case, the second way.
In this particular case, this was probably easier, the second way. So that was just to show you how to use the product rule and that we should get the same answer as we would if we didn't use the product rule. Now let me give you an example of a function where you have no choice. You must use the product rule, all right? So how about this? How about x to the 4th sine x? Do you see a product?
Yeah.
Okay, the product is occurring right here, right? And so we could label one of these functions if we want. We could say, hey, this is going to be my f guy, and this is going to be my g guy. And you don't have to use F and G. You could use any two letters you want. So the derivative, according to the formula, is F prime G plus G prime F, right? That's my formula. And so let me write down F, which was x to the fourth, and I'm going to take its derivative. So I just wrote down F prime, then times G. G is what? Sine x, so times sine x, plus now G prime, right? So I'm going to write down G with a prime, and then times x to the fourth without any prime. That's just me writing the formula down. You will get to a point, probably by Monday, where you don't have to write this formula down. You're just going to do it mentally, all right? But I just want to make sure everyone sees where everything comes from. I have a habit of going too fast through this. So derivative of x to the fourth is? 4x cubed. And then sine x, right? Don't touch it, just leave it alone. Then what's derivative of sine x? Cosine x. So I have plus cosine x times x to the fourth. And I can put these two together and make it x to the fifth? No, right? Be careful here. That is the argument. We call it the argument of the trig function. It is trapped. That x is trapped inside the cosine. This x to the fourth is completely separated from it. So just to be sure there's no confusion like that, what we usually do is we'll pop the x to the fourth out in front of the cosine so that you don't make that mistake of trying to put those together. There's your derivative. Make sense? Well, it'll get a little more challenging. Okay, let's try something else. How about let me use some different notation. How about f of x equals x squared tan x minus cotan x. So I would like for us to find the derivative of this. All right, so what do we have going on here?
Got the first two in the product.
This is a product right here, right? But I actually have two terms.
The second one, you can take the derivative.
Yeah, am I allowed to take the derivative of this separately from this? Yes, because there's subtraction between those. So I'm going to just do this derivative on its own. But when I go to do this derivative, I have to recognize that there is a product between those two. And so I must apply the product rule to these two. Understand? Yes? Okay, so let's try and do this without me writing any fancy letters down. If this is where my product is occurring, right there, and I want to take the derivative of it, it should be the derivative of the first one, right, times the second one, plus the derivative of the second one times the first one. So let me write that down. It's the derivative of the first one times the second one, plus the derivative of the second one times the first one. Boom. That's my product rule on the first piece right here, right? Derivative of the first one times the second plus derivative of the second one times first. But I still have to do the other one out here. So minus, and I do need to still take the derivative of cotangent x, don't I? Okay. Yeah, that's one of the ones from last class that we need to, well, we don't necessarily know it, but we need to know where it is on our formula sheet in case we forget it. But let me take care of these first. What is the derivative of x squared? 2x. So this is 2x tan x. Plus, now the derivative of tangent x is one I suggested you try and memorize. Close? Just secant squared x. So this is secant squared x times x squared, and then those come together? No, be careful. You got to be real careful with these trig functions, with these powers and x. They do not go in there, all right? You cannot force anything inside of a trig function like that. Minus, what's the derivative of cotangent to x? Negative cosecant squared x. So this becomes negative cosecant squared x, like that. And I'm going to do one last line of cleaning up, and then I'll be done. So I'll write 2x tan x. I don't like this x squared here. I'm going to push it into the front here. Plus x squared secant squared x. And then this becomes minus minus is plus. So plus cosecant squared x. There we go. You like it? Yeah, you like it? How about this one? H of t is sine t cosine t. You know what? Let me add one little thing to this. Let me put a 2 in front of this. Just for fun's sake. What do you see happening here? You could look at this as 3 products, but it's a constant. So it's going to come with, it's attached to a function though. Constants by themselves, the derivative is 0. So yeah, it's going to come along for the ride, but here's where I'm going to do it. Here's my product, right? Let's look at it kind of like there's a product there. My 2 functions are this with the 2, and then this one just the cosine. Do you see what I'm saying? That 2 is going to just be attached to the sine and just come with the sine. If you did this as 3 things, it would get ugly because you would have derivative of a constant and 0. So I do want to do one of those. Just wait, okay? All right, so you ready to do this? All right. The derivative of this should be, since it's a product, the derivative of the first one, right? Derivative of the first one times the second one plus the derivative of the second one times the first one. Are y'all kind of getting that little jingle in your head? Derivative of the first times the second plus the derivative of the second times the first. What is the derivative of 2 sine t? 2 cosine t. What about, wait a minute, hold on. I told you that the derivative of constant was 0. So why is this not just all 0? Because it's attached to a function, it just comes along, and then derivative of sine is cosine. So there you go. And then here I have cosine t. Then plus, what's the derivative of cosine t? Negative sine t. And then times 2 sine t. Now I can do a little more cleaning up on this. Cosine times cosine is cosine squared. So I can write that as 2 cosine squared t. And then what about that second term? What's that going to become over there? Negative 2 sine squared t. That looks pretty close to something, doesn't it? Like if that was a plus. Yeah, if that was a plus, it would be something. Right? Look, if I do this, if I factored out a 2, cosine squared t minus sine squared t, isn't cosine squared t plus sine squared t an important one? It's 1, right? You better know that. Okay, if that's a plus, everyone here better know that that's a 1. All right? Okay, good question. What if I factor a -2 out? Would it change that to a plus? Well, it would change that to a plus, but it would change this one to a minus. And so you still couldn't get it that way. So this is not the Pythagorean, unfortunately, it's not the Pythagorean identity. It's not equal to 1. But is it equal to something? Look on your formula sheets.
Who's saying that? Who's saying that?
Who's going to find the formula for cosine squared t minus sine squared t?
Equals cosine 2x.
Is it? Cosine 2. So
Yeah, cosine
give me the formula the way it's read on that sheet. Cosine
2x equals cosine squared x minus sine squared x.
and then there's 2 more that it's equal to, right?
Yeah.
But where is that on the formula sheet? What reference page? Reference page
Reference page 2, that would
Two.
be double angle formula.
double angle formulas. So you recognize that maybe now? Pre-cal? So this right here, right? This right here should just be 2 times what? Cosine 2t. Don't use x, okay? The formula has x, we have t's. That's just 2 cosine 2t.
Which answer would you accept?
This would be okay. This would be okay. That is the derivative. But the reason I'm showing this to you, I have a purpose for this, okay? There is a major purpose for me giving this to you. All right. But are we clear up to this point? Let me go back and look at the original function. While you've got that formula sheet out, do you recognize that? 2 sine t cosine t. Look one line above where you just were. Isn't that sine 2t? Isn't that sine 2t? The original function is sine 2t. Because sine 2t is equal, or on your formula it says sine 2x is equal to 2 sine x cosine x, doesn't it? So I could have just started this entire problem off by rewriting the original function as sine of 2t. Do you agree? Now, yeah, so let's talk about this. What you would probably want to do here is just say, hey, what's the derivative of sine 2t? And your answer would probably be cosine 2t, right? But that's incorrect, because it should be 2 cosine 2t. Somehow, just taking the derivative of that and getting cosine 2t is not right. And the reason why is because we have functional composition here. You have a function inside of a function. The inner function we have is 2t. And that's being plugged into a bigger function, which is sine t. And the way we take derivatives of that is different than what you would naturally think. It requires a rule. It's called the chain rule. Be here Monday. We will do that. All right? But what I want you to see is that it's not as simple when you have a function inside of a function like this. It's not as simple as just, oh, this is just cosine 2t. You can see the answer should be 2 cosine 2t, which means there's something else that we have to do. Got it? Be here Monday. All right, let's do another example. Oh, you know what? Are you ready for quotient rule? Yeah, let's get to quotient rule. Now, the quotient rule allows us to deal with division. So we have a rule for multiplication that's called the product rule, and now we have a rule for division. And it says, if you would like to take the derivative of a quotient, you are going to have a top function and a bottom function. A top one and a bottom. Remember, for product rule, I was saying that we had a first function and a second function. First and second. For quotient, you're going to hear me saying top and bottom. Okay, we have a top and a bottom. So what is the derivative of this? Well, it would be great, again, if it was just derivative of each one and you're done, right? It's not, though. It's really ugly. It's the derivative of the top one times the bottom one without a derivative. Hey, does that look familiar? It's kind of like this one, right? Is derivative first times second? But instead of plus, we put a minus. And then we do derivative of the bottom one times the top one. Hey, does that look familiar?
Yep.
That's exactly the product rule, isn't it? Isn't this exactly the product rule? But with subtraction. With one additional huge thing. The whole thing must be divided by the bottom function squared. With no derivative. Just whatever the bottom is, rewrite it and square it. That's the formula. So do you all see that if you memorize the product rule, the only difference between the product rule and the quotient rule is a minus sign, right? And divide by g squared. That's the only additional piece of information that you need to remember. Agreed?
Yep.
Okay. Now with that in mind, I'd like to write down the book's version, okay? If you look in your formula sheets on reference page 5, they have written down for the quotient, well, for the product rule, I don't even want to put it on the board. I'm going to put it over here. The book writes f of x g prime of x plus g of x f prime of x. That's what they use for the product rule. I'm put p out here for product rule. And for the quotient rule, they put g of x f prime of x minus f of x g prime of x all over g of x squared. That's what the book has. Now let me explain to you why I do not show you the book's version and I go with this version. Hopefully I made it clear to you that there's really not a big difference between the two formulas, right? It's just a minus sign divided by g squared. But if you look at the book's version, which is correct, it's still the same answer. What they've done, let me write my product rule down here. F prime of x, g of x, plus g prime x, f of x. That's a product rule I'm giving you, right? Theirs is, my first one here, right, is their second one, and we have flipped order. But it's multiplication, so it doesn't matter, right? So our two formulas differ by flipping these and then switching like that, right? And then their quotient rule is almost mine, except this is flipped, right? This is flipped. So our quotient rules are pretty much the same. The reason I don't like this is because to me, when I step back and I look at this, these look like two completely different formulas I have to memorize. Right? One of them is fg prime. This one was gf prime. I'm going to screw that up. You know, when I'm trying to do this, I'm going to screw it up. Because I'm going to be like, wait, was it the product that was the f and then the g? I'm going to mess it up. So to me, this is confusing and it looks too different to me. Do y'all agree with that or no?
Yeah.
Okay. This to me, as long as I memorize this, then to go to quotient, I put minus and divide by g squared.
That's pretty counterintuitive. I mean, even though it means the same thing.
Yeah, there's a reason why they do it. It's because when you prove it, when you prove the actual product rule, this is the way it comes out. It comes out like this. So, but you can rearrange it. So, most books do this. But again, remember when we were talking at the beginning of class, I try and teach this in a way that it made sense to me. For the longest time I sat there and I had these two memorized, two different formulas, and I was like, and as I advanced through math, I was like, wait a minute. It's the same freaking thing if I do that, right? So I realized, wow, and why don't you just do it this way? It's easier to remember, right? To me it is. I'm not a memorizer. I'm not one of those people who can like just look at stuff and memorize it. I don't like that stuff. Okay, here we go. Quotient rule in action. We'll start out with the baby one. There we go. There's a nice little quotient for you. And I'm going to erase these so that you don't put those into your brain. All right, so we have a top function and a bottom function, right? Top and bottom. We could say the top is f, the bottom is g. When I go to find the derivative, it's going to be, what's first? The top one's derivative, right? Okay, I'm going to write that down. It's the top one's derivative times the bottom one, no derivative, right? Then what? Minus the bottom one's derivative times the top one. Now look, this is one of those areas where if you go get help, tutoring, you go to tutoring lab, most likely the tutor's going to want to do it this way, the way that the book. That's the way they probably have it still memorized. If you want to, you can, but I would suggest you try and remember it this way. I think it's easier long term. Is that it? I'm done? No. Over, don't forget this part, over the entire denominator, just write it down, don't take a derivative, and then square it. And there it is. We just have to take some little derivatives now. And these derivatives shouldn't be so bad. 2x plus 1. And do I need that in parentheses?
Yeah.
Yes, because it's two terms, right? And I'm about to multiply it times x cubed plus 3x, which I didn't touch. Then minus. And now 3x squared plus 3, and then I'm multiplying that times x squared plus x. All of this over, and don't try and expand this, okay? Just leave it alone. There we go, squared. This is what we would consider, and you'll hear me say this sometimes, I consider this the raw derivative. That is the raw version of the derivative. That is it. We do need to be able to manipulate it algebraically. That means we need to be able to multiply things out. So when you're doing your homework, what I think you need to do is get your raw derivative and then look at the back of the book and look at the answer. And it's going to look like you're wrong, okay? And your job is to try and turn that into the back of the book's answer. On your homework solution videos that I put out, a lot of times I do not take these and simplify them completely because it's algebra at that point. But for this one, let me show you what I mean by that. I could multiply this out, right? I could then go multiply this one out. And I could clean them all up and put them together, collect like terms, right? I could do that. So let me do it. So let's see what I would get here. 2x times x cubed, 2x to the fourth. 2x times 3x is 6, x squared. And then plus x cubed, and then plus 3x. Do you all agree?
Yep.
Okay, that's this distributed. Now on this one, I'm going to go kind of fast here. I'm going to go 3x squared times x squared, which is 3x to the fourth. But I'm subtracting it, right? So minus 3x to the fourth. Then the next multiplication, 3x squared times x, 3x cubed, but then subtract. So minus 3x cubed. Where am I at? 3 times x squared is 3x squared, but then subtract. And then finally, minus 3x. So there's the numerator, right? All over the denominator squared. The reason we want to be able to manipulate this algebraically is because this is the derivative, right? And like the first problem we started class with, we were trying to figure out where that slope of that tangent line was 3. Remember that problem that we started with? Or we might want to know where the slope of the tangent line is 0. That means you're going to have to take this and set it equal to a number, which means you're going to have to solve an equation. And when we solve equations, this would be really ugly to try and solve. So we try and clean it up a little bit. Now I know that still looks pretty ugly, but let's see where we get here. What do I have? Negative x to the fourth on top? I believe. That's those two together. Then x cubes minus 2. X squareds, 3 of them. And x's, they're gone. They cancel each other out. So that's it on top. And then x cubed plus 3x squared. You could factor, but let me stop here, okay? We could pull an x out, cancel it out. We could do that, right? Yes. We actually could have done that in the very beginning. You probably missed that. Maybe you did, maybe not. You could have factored an x out and canceled, and then it would have been a little easier to work with. But there's our derivative, right? What if someone now came along and asked you to figure out where the derivative was 0? You look at this, and you'd say, let's set that to 0, right? I'm boxing this. I'm saying that's my answer for right now. If I asked you to set this equal to 0, then let's see if anyone remembers this, or if this was stressed in your college algebra class or any class that you were in. Let's see if you have a fraction and it's set equal to 0, what is the only thing you really have to look at? Other way. The numerator.
Because you can't have division with zeros.
Well, it's because of this. If I ever have a fraction equal to 0, I only ever need to look at when is the top 0. Because if I have this, can't I always multiply both sides by b?
Yeah.
And this b would cancel, and then over here 0 times b would be 0. And you just get a is equal to b. I mean, sorry, a is equal to 0, right? So when I have this fraction and I want to know when it's 0, right? Then all I really have to look at is this. And I'd be asking myself, when is negative x to the 4th minus 2x cubed plus 3x squared equal to 0, right? That's what I'd be asking. And could you solve that? I hope so. Let's see. Let's factor something out. What do they have in common? X squared? Let me pull a negative x squared, because that'll change that to positive x squared plus 2x, and then what? Minus, I pulled a negative x squared. Man, I completely made this problem up. The fact that this is actually going to factor is purely chance, okay? I didn't even think we were going to go to the point where we were going to set it equal to 0. But can you appreciate why simplifying it was worth it? Because I was able to just now grab that numerator and go set it equal to 0. So what do we have here? X squared. This is x plus 3, x minus 1 equals 0. And so I have 3 answers. 0, that's setting that to 0. Negative 3 and 1.
And that's the answer to what question?
When was the derivative 0? Now we do have a little bit of a problem, and that's this one can't be there because it's not in the domain of the original function. You can't plug 0 in. You have an asymptote there. And do you understand what I'm saying?
Yeah.
So if I graph this, if I graph this original function, which was x squared plus x over x cubed plus 3x, I'll get all that crap out of there in a second. Delete, delete, and delete. Can you all see it? That's the graph, all right? At -3 and at 1, we should have something interesting happening. So let's see. If I go to extremes, look at this. This actually comes down, right? You can't tell from the picture, and then it actually starts going back up there. This is the lowest point right here. And it matches up. Can you see it says -3 there? Okay. We knew that that happened there. We found out that that happened there. Also at 1, right here, at 1, highest point, and then it comes back down. 1. So we were able to recover those two interesting points on this curve using the derivative. Make sense? Yes. We're going to have an entire chapter on that. So. Yes, most of the problems they give you won't simplify, but yes, always look at it and see if you want to do something algebraically to it first. Right now you need to focus on using the rule and trying to simplify your answer to make it look like the back of the book. All right, let's look at another one. How about this one? What's my time look like? Y is tangent x. What's the derivative? We know that the derivative of that is secant squared x. Do you agree? Because why? Because I told you. Because it's on a formula sheet, right? Reference page 5, formula 15. So look. Last class, did I prove? I think I did. I know I did. That the derivative of sine was cosine? Yeah. I proved it using the limit, right? Yeah. And I showed you that you could very easily do cosine the same way, but I didn't do cosine because I didn't have time. And then I told you the rest of these, we're just going to know what they are. But I'm actually going to show you now why this is secant squared. But I'm not going to use the limit. Here's what I'm going to do. I'm going to rewrite this as its definition, because I've already proven the derivative of sine and cosine to you. Well, I proved sine and I think you believe cosine. Then I can use that and treat that as a quotient. Can't I? That's a quotient. So if I apply the quotient rule, it should be the derivative of the top, good, times the bottom minus derivative of the bottom times the top, right? All over the bottom squared, which you could write as, you could write that this way, right? That's the same thing. And now just take some derivatives. Top left, derivative of sine, cosine, times cosine, minus derivative of cosine, negative sine. So you're going to have minus negative sine times sine x again, all over cosine x squared. Right? And that just becomes cosine squared x plus sine squared x over cosine x squared. And one of my students in my other class asked me at this point, can I just cancel these two? Now I have to have a cosine squared over here also to cancel. But from pre-cal, that's one of the big identities. Cosine squared x plus sine squared x is 1. Yeah, and 1 over cosine is secant. So this is secant squared, which is that. So once we were able to prove that the derivative of sine and cosine were what they were, then you could get tangent by using the quotient rule. You could do this for the rest of the